I'm starting by thanking the organizers, and original title of my talk was different. Then Probal insisted that I also talk on the similar topic. I'm running this video. So here it is homogeneous nucleation as opposed to what Probal showed, that is heterogeneous nucleation basically. And what you are seeing here, replication or Mpemba effect is reproduced. Here, the student Shomik Ghosh, he did the work for water, and water configurations from all these three temperatures, they are belonging to vapor region as well as liquid region, depending upon the pressure that we are using, have been quenched to a very low temperature, that is 230 Kelvin. And you can see that the ones with higher temperature, they are getting into the ice phase earlier. Okay. And this is half of my talk, and in addition to water, I will talk about Mpemba effect in some other systems also, like magnetic systems, Ising and Potts model, as well as active flocking in Vicsek model, that is living matter system. Okay. Okay, let's, and these are my collaborators, you might have seen already. Mpemba effect is, it's not that Mpemba is the first one who discovered it. It was known from the time of Aristotle, and Mpemba basically accidentally rediscovered it during a cookery class when he was a high school student. And if you go to this paper by Mpemba and Osborne, you'll see that Mpemba's friend who used to make and sell ice cream, they already knew the effect. They needed it. I mean, they knew, and that's why they used to heat up before putting water inside the, or milk mixture inside the refrigerator to make ice cream quicker. Okay, and Mpemba is the bolder one who could ask this question from his counterintuitive observation to his teachers, friends who basically ridiculed him. And then he came in contact with this gentleman, Dennis Osborne, who along with Mpemba performed some more controlled experiments, and this is the result from this experiment, which was published in this not so well-known place with this interesting title. And from Probal's talk as well as from Rajesh's talk, you have seen already this picture, this diagram. For a large range of starting temperature, the cooling occurs, the freezing occurs faster for hotter temperature. Okay. Now, in the literature, there has been this effort of generalizing the effect. Take any system, not necessarily water or vapor, and ask this question, is there any dependence of the relaxation time on initial temperature for reaching the equilibrium corresponding to the quench to a lower temperature? Okay? And if you look at these publications and the systems these people have considered, they are related to combination of ferromagnetic and antiferromagnetic interaction that may lead to frustration, metastability, etc. And they were probably motivated by the scenario in water where metastability is a severe problem when you want to, starting from the liquid or vapor phase, you want to make ice. Now, in a recent work that Probal briefly mentioned about, we took a system, much simpler system, without any frustration, inbuilt frustration. That is the pure ferromagnetic Ising model, that's J greater than 0. And we use the following protocol. Basically, you have this magnetization versus temperature phase diagram, and you prepare your systems at various different initial temperatures in the paramagnetic phase, and then quench all the systems to a fixed final temperature Tf and look at the relaxation, which one relaxes faster than the others. And it appeared that, and we observed that the hotter paramagnets relaxes or turns into ferromagnets quicker than the colder ferromagnets. And this basically took several people in surprise. Immediately after the publication, I kept getting queries from people who already started working in this area. And they said that how is it possible? There is no frustration in this model, no impurity. And that's what the objective of our work. We wanted to verify whether the inbuilt frustration in the Hamiltonian, or for that matter metastability, is necessary to reproduce such kind of phenomena, and it appears that it is not. So I will show some representative results from similar work that is in arXiv. Yeah, so that's the Potts model, Q-state Potts model, 5-state Potts model. What you see here, these are two representative evolutionary pictures. You start from, say, two different initial temperatures and quench below the critical point, and you see that the hotter one goes to the ground state or final equilibrium quicker than the colder one, colder temperature. And here is the averaged out result. This is these are a couple of combinations of runs. And here what is shown, the decay of energy as a function of time for various different starting temperatures. And for the sake of clarity, we have basically divided into two subframes. The upper one is for early time and the lower one is for later time. And you can see there is clear reversal of trains in the appearances of various different colors, that's plots. That means there are crossings. This implies that the hotter one is going to the new equilibrium quicker. Okay, that means there is Mpemba effect. And we see the similar phenomena in active matter system also, modeled by this so-called very popular Vicsek model. And so I am not going to discuss this thing. So here what is happening, this Mpemba effect in this kind of systems are driven by fluctuations that are critical in nature. Okay? And it's basically appearing because of the differences in critical fluctuations at different state points. Okay? And there exists nice universality also. So here what is Mpemba effect is basically related to the delay for colder temperature or for at some other related to some other parameter in the approach to equilibrium. And here we have plotted such kind of a delay time as a function of the equilibrium correlation length for a class of models. And you can see nice collapse of data for coming from different types of models or systems. And here we have not put the Lennard-Jones system, that also falls in the same category, in the same universality. Now we go back to the water. So we start, say, this is some here are the protocols. We use NPT simulations at approximately 4 atmospheric pressure, and we quench our systems from vapor as well as liquid phases to form ice. Okay, I told you already 230 Kelvin, and here is the reproduction of the Mpemba curve. Okay, and I show the video again. Here is Mpemba's Mpemba and Osborne's figure, and here is our figure. It's quite comparable. And as opposed to, as I have mentioned, Próbal spoke about heterogeneous nucleation, and this is homogeneous nucleation. With that, I would like to stop, and if there are any questions.
Is the adiabatic or the non-adiabatic?
So cooling description is the following. So we try to do instantaneous cooling, but the protocol, the LAMMPS program, it takes a little bit of time to go to the final temperature. Yeah.
So Subir, I have one quick clarification. As you mentioned in your slide, in simulations, it's actually hard to observe.
You know about this model very well, and you wrote this TIP4P ice. Okay, so what we did, I am guessing that I understood your question.
Okay.
In simulations,
I could also say it. How did you crystallize?
In simulations, it's extremely difficult to get into the ice phase with whatever model you studied, and this TIP4P ice is one of the better models. And Srikanth wrote a comment or something like that, commentary, news and views article in Nature, when first freezing in this model was observed. Okay, by this. So he forgot.
On nucleation, yes, but not on. Yeah.
You forgot yourself. Now, the question you asked, so nucleation goes in the following way. Yeah. Nucleation requires fluctuation to happen. And larger the system, the scopes are that in one or the other places there will be some disturbances and can lead to nucleation of ice or for that matter of any other type. Now, for that requires large systems to get it more easily, but larger systems on computers is very difficult to simulate. So we took only 96 water molecules and compromise with time. Okay, so this way it worked. Basically.
I see. Okay, nice. So,
Sorry.
So it's a trade-off between system size and time.
nice. No, so Sanjay, sorry. No, I mean, in general, right, this Mpemba effect should not be surprising if the pathways to the final state are different.
Yeah,
It's
so
only surprising.
I'll spend some time on that. So I go back to this protocol.
Yeah.
Okay, so Mpemba effect, why is it surprising? Is basically this one is equilibrated, getting equilibrated faster. That means it's more distant from the final state point. It's like, say, I'm giving the lecture here, somebody is coming from IISc, somebody is coming from Mysore, and Sanjay is coming from Delhi. But Sanjay is arriving here earlier than Rahul coming from IISc. Okay, but that can
happen in
that's the surprising aspect, and that can happen if there are modes of transportation, which is, say, Rahul is walking and you are coming by a car from Mysore and Sanjay is coming by aeroplane. Okay, so it's about mode of transport. Okay, going back sometimes can open up channels or provide you with some. So it's not like when you are coming from here to here, it's not a quasi-static process that you are passing through all the state points. Exactly. So that way it's not surprising, but it's a complicated issue we need to investigate it. And in water in particular, is the metastability that is giving rise to.
No, I just wanted to point out that in the case of nucleation in general, there is a well-known non-monotonicity of nucleation rates, which comes from the mobility. Usually, this is discussed in terms of the mobility at the temperature where you're sitting, but because you're quenching different structures, right, to a given temperature, the mobilities are in fact very closely related to the parent's state point. And how much is it understood what role that plays?
Well, I'm new in water literature, and this is our first work. It's not even on an archive. Okay, and we are trying to understand this thing. We are doing analysis, but okay, it's premature. So I don't like to say anything on that. So what is happening? Whatever starting temperature you are taking, they are kind of coming down and getting stuck in some sort of metastable, close metastable states. And the question is, how long a system stays there? Jumps from that metastable state to the final ice phase. Yes, Sanjay.
No, I just want to say, it seems like it's not clear to me the completion of a phase transition is sort of a finite size effect, right? In an infinite system, the phase transition never completes.
Yeah.
So is the Mpemba effect a thermodynamic statement about the speed of the phase transition, or just of the completion of the phase transition?
It can be both. Both are equally important, I think.
We'll discuss it.
Yeah.
Let us thank the speaker.